Very pleased to have one of our own speaking today. Edward Lee is going to talk about a new center that's just been awarded that's centered here at Berkeley. Let me do the intro. It's a privilege to introduce Edward Lee. He's the Robert S. Pepper Distinguished Professor and former Chair of the Electrical Engineering and Computer Sciences Department at UC Berkeley. His research interests center on design and modeling and simulation of embedded real-time computational systems. He is director of CHESS, the Berkeley Center for Hybrid and Embedded Software Systems, director of the Berkeley Ptolemy Project. He has co-authored of 5 books and numerous papers. He's led the development of several influential open source software packages, most notably Ptolemy and its various spin-offs. His bachelor's degree is from Yale, 1979, master's from MIT, and PhD from UC Berkeley in 1986. From 1979 to 1982, he was a member of the technical staff at Bell Telephone Laboratories in Holmdel, New Jersey, in the Advanced Data Communications Laboratory. He is a co-founder of BDTI Inc., where he is currently a senior technical advisor and has consulted for a number of other companies. He's a fellow of the IEEE and was an NSF Presidential Young Investigator and won the 1997 Frederick Emmons Terman Award for Engineering Education. Very distinguished. Well, thank you, Edward. Thank you for agreeing to come and talk about this very timely topic. And we look forward to hearing about it.
Thank you, Ken. Yeah, so it's a real pleasure to be here. This is the announcement for this wasn't sent out until yesterday because I had gotten unofficial word that we were getting selected for this center, but it was not supposed to be leaked. And so, we reserved the slot to kind of tell you what's going on hot off the presses. But this is, it's a little uncomfortable for me because I'm used to talking about work that I've done. And here, I'm not going to be talking about work that I've done. In fact, I'm not even going to be talking about work I'll be doing. I'm going to be talking about work that all of these people are going to be doing. And my part of it is a rather small part of that. I'm not at all used to giving talks like that. So I apologize if I, don't get it right. But in fact, the talk that I'm going to give in many ways isn't my own. I've drawn material from a number of people on the team, most notably Jan, who will recognize a lot of the slides, I think. I also would like to point out, in case you hadn't noticed, that on the front page of the Berkeley campus website, which doesn't show up here, sadly, it shows up on my screen here. But anyway, our center is mentioned on the berkeley.edu page. Okay. So this is a brand new research center that will be launched in January. It's a center that's funded by FCRP, which is an acronym that stands for the Focus Center Research Program, which is organized by SRC, the Semiconductor Research Corporation, which is funded by MARCO, which is a Semiconductor Industry Association, and DARPA. Okay, so that's a lot of acronyms. I didn't even tell you what DARPA stands for, but I assume everyone probably knows that one. So it's a pretty big deal. This center is going to be led at Berkeley. There's a total of 9 universities involved. And it's a very interesting team of people. So what I'm going to try to do is give you a little bit of a perspective on what the center is trying to accomplish. So the backdrop for this is, of course, information technology, which has changed everything in our lives. But I picked this picture to emphasize that information technology is primarily about the interaction between humans and information. That's really what it's about. It's human beings who communicate with one another through this technology, access data repositories, libraries, and so on. This interaction with information, and as a consequence, the interface between the physical world and the information technology world is primarily about conveying information. The input devices we have are keyboards primarily, so we put in ASCII text, cameras, so we capture images, and store them somewhere. And the output devices from the information technology world are displays and audio, which are primarily there to provide stimulus to the human brain, okay? So that's the backdrop. The focus of the TerraSwarm Center is to say, well, that information technology world is in the process of transforming itself to now much more directly interact with the physical world. So it's not just about information, pumping information in and out of human brains, but also about getting data from our physical environment and also affecting our physical environment. So, and many times even without human intervention, okay? So we see this as a potentially very big change coming in this world, and the focus of this center is really to address both the opportunities and the risks and the potential pitfalls that can arise from that change in technology. Now, today we all know that a lot of the information technology world has been shifting from desktop computers or enterprise-scale computer rooms into the cloud. And there's a lot of reasons for this. And when this started happening, I kind of thought that the primary reason was cost. That there's economies of scale in putting your computers in a huge data center, virtualizing your machines to reduce your maintenance costs. And in fact, there is demonstrable evidence that in fact, it does have that effect. The cloud is a significant cost reduction tool for providing computing infrastructure. Here's a particular market study that gives some numbers. I have no idea about the veracity of these numbers, but it kind of looks impressive. And if you look at these numbers, you can see, wow, you could be spending somewhere between 15 to 30% of what you're spending today if you just move all your stuff to the cloud. So you clearly get efficiencies from aggregation here, the aggregation of computing resources into the cloud infrastructure. Yeah, Bernard.
Communication is the
I don't know what assumptions they made in this study, okay? I think obviously the cloud assumes reliable, pervasive, high bandwidth communication because otherwise you can't really take advantage of this aggregation. But I'd like to argue that this is actually not the primary benefit that has emerged from the cloud. And the primary benefit that emerged from the cloud is one that I think caught us all by surprise. Or at least it caught me by surprise, but I think it caught much of the world by surprise as well. That the primary value came from the data aggregation, not from the aggregation of resources and the centralization of resources, right? So the emergence of social networks and all of these kind of the new dot-com bubble that's happened is around interactions that have been enabled by the aggregation of data that comes from a huge multiplicity of sources. Okay, this is actually where I think this benefit I think dwarfs the efficiency benefits that we've gotten from the cloud because it basically makes information much more valuable. So if you have information about the performance of your company, right, in your enterprise servers, if you can aggregate that data in a safe way with data that tells you how other companies in your industry are performing, you can get insights into the trajectories of an industry that you can't get from the isolated data by itself about your single enterprise. Okay? And of course, we see in social networking that it really enables a kind of activity that wouldn't otherwise have been possible. So the data aggregation, I think, is something that we expect in the TerraSwarm Center is also going to be a big benefit coming as this IT world reaches out and starts touching the physical world. So instead of having, for example, sensor streams we've got sensors all around us that are modulating the behavior of the HVAC system in this building, okay, that's trying to keep us comfortable. That information, for the most part, however, doesn't go out beyond the boundaries of the building, okay? And it doesn't get aggregated with anything else. It's a very stovepiped kind of isolated system. This is going to change, and we're convinced it's going to change, that these sensor streams are in fact going to provide data that can be aggregated in ways that can provide benefits similar to the data aggregation that has happened in the social networking world. Okay? Now, there's a lot of interest in the industry today, of course, on where the money is being made today. And the money is being made today hand over fist with handheld devices, right? So I talk about the 20-year overnight revolution of wireless handheld devices. It took 20 years. Why did it take 20 years? Well, because Bob Broderson and Jan Rabai invented the iPad 20 years ago, roughly. And so when the iPad came out from Apple, we all called it the InfoPad 2.0. But these things take time, right? But these things have clearly taken off, okay? So there's a huge industry focus. Now, of course, when you have an industry focus, I think there's also, it raises a red flag, right? There's an obsessive focus on where you can make the money today, but that can also result in blinders, that you put all of your energy into this one thing that is yielding the revenue today, okay? And it is clearly yielding revenue today. You have these, devices that are exceedingly profitable. So people view these devices as the interface to the cloud, okay? So they're at the edge of the cloud, and the idea, many people are speculating that these guys, that our personal computers will actually disappear and be replaced by these handheld devices. If you do email regularly on an iPad, you'll realize we're not there yet, okay? That there really are significant advantages to an actual computer still. But nonetheless, it's clear that these devices provide an interface to that cloud world. And even the personal computing devices have shifted their focus to being an interface to the cloud more than being standalone computing devices, okay? Now, huge growth in this area, tremendous amount of profitability, okay? So what's happening in the trajectories that have to do with the TerraSwarm space, which is in how the information technology world interacts then directly with the physical world? So there's been speculation for several years, okay, about the potential benefit that we can get from tremendously improved technology in deploying sensors that can measure the physical world and can be operated at battery power so that they're very cheap to install. You just glue them to a wall somewhere, and they communicate wirelessly with one another and form ad hoc networks. These things have been under development and have been tremendously improving for 15 years at least, okay? Our colleague Chris Piester here coined the term in 1995, smart dust, to refer to this, pervasive sensors that could be deployed in our environment and would, be able to form ad hoc networks and provide data streams about the world. And of course, as often happens when you have a technology like this that's very exciting, people make projections about the business value of these things. And here's a business projection compared to the actual reality, okay? So this was an estimate that was made for the market value of wireless sensor networks was going to be somewhere approaching $6 billion by 2010. And the reality was that the market value of the wireless sensor network industry was only about $439 million. It fell dramatically far short of the projections, and the growth in this industry has been much slower than people expected, okay? So Jan did an analysis of this and came up with what I think was, to me, it was kind of an amazing insight, which is to try to figure out why it is that the growth has been so slow. I mean, it seems like if you have this technology that you can, put sensors all around you and replace a lot of these things that are wired, like that thermostat that's right there on the wall. Most of you can't see it because it's on my side. Rather expensive thing to install, right? you would think that if these things really have this much potential, that there would have been much more rapid growth in this area. But there's been a number of limitations, okay? Some of them are very technical limitations, right? Just getting the battery life down, right? I mean, that thermostat will probably operate without flaw for 20 years, right? And having a battery-operated device that you can just install and have it run for 20 years is still a pretty daunting challenge, okay? But I think that the real reason is this one that Jan identified, which is that there's a fragmentation in this industry that doesn't, the data aggregation that we see in the social networking world is not yet possible in this industry. You can't just recruit data streams from sensors that are around you and use them for a new purpose, which is what you have the potential for doing in the social networking world, right? The fact that in the social networking world you can recruit data streams in order to do what some people might consider horribly evil things like targeted advertising or something like that. That kind of capability hasn't existed in this wireless sensor network world, primarily because the systems that are deployed out there are stovepipe systems, single vendor systems without open interfaces. It's exceedingly difficult and costly to combine a multiplicity of sources of information from sensors, okay? So the observation and the premise of the Terra Swarms project is that can be changed, okay? That we can actually, by providing an appropriate abstraction layer on this world of sensors and actuators that will appear on the network, okay, we can provide an app programming framework that will enable then creative people like, you know, the millions of developers who develop apps for this platform. We'd like to see millions of creative developers developing apps that recruit and leverage sensors and actuators in our physical environment. Now, so the view there is what Jan calls the swarm at the edge of the cloud. Yeah, okay, so the swarm at the edge of the cloud is the point at which the information technology world touches the physical world in ways that are not just about pumping information in and out of human brains, but rather about measuring and controlling and affecting the physical world. That's the swarm at the edge of the cloud. Now, this is a pretty daunting problem to address this, okay? So here's kind of a scatter plot of some of the technical issues that come up in Terra Swarms. Looming rather large are security concerns, right? If you have sensors all around you that exist on an open architecture so that an arbitrary creative app programmer can recruit them and gather data from them, this could turn out to be not such a good thing for many obvious reasons, right? Security and privacy are going to become absolutely central issues in how you proceed, okay? I'll try to give you some of the insights that the people on our team have about how to address those problems a little bit later on, okay? But right now I'm just going to try to kind of lay out what the landscape is for the problems. There's obviously still problems in wireless sensing and actuation. We still have problems with the energy consumption in these devices, the durability. We have problems with how to design these systems. What kind of architecture should we use? The Terra Swarm systems that we envision are hugely heterogeneous. They're going to involve a multiplicity of very diverse technologies, and we have pretty good technology for developing much more homogeneous systems. So, for example, if you're doing web development, okay, we have some very well developed engineering tools that you can use, but it's a pretty homogeneous design environment, and at least compared to the design environment that we will experience with Terra Swarms. There's big problems about how you compose services, right? If you're relying on a multiplicity of sensor and actuator services, how do you combine them in interesting ways, particularly when they're coming from very different sources? There's problems that have a big data nature, okay? So if you have a lot of sensors they're going to feed you a lot of data. You don't want a lot of data. You want a little information, right? So the question of how you extract a little information from a lot of data becomes the central problem. So there's a number of challenges. Here's a list of them that we kind of highlighted in the proposal for this project. Data collection and storage, simply because of the volumes involved and the fact that we still don't know how to extract information from these huge volumes of data. And as a consequence, we're probably going to end up handling much more data than we really should be. Data integrity, how do you trust data that you're getting from sensors? What does it mean to trust it? Okay. Safety of physical interactions. If we're allowing app programmers to recruit actuators that affect the physical environment, traffic lights in the city, should we allow those to be affected? You know, there could be some interesting problems, right? The sheer complexity in these systems, the fact that unlike many of the designs that we deal with today, a lot of engineered systems that we design today, we design them, we test them, and we ship them. Okay, and we may revise them then, you know, a few months later, ship a new version. But the TerraSwarm systems are probably not going to be like that. They're going to be systems that are kind of continuously changing in the field, and so the design problem changes. In some sense, design technologies that you would use, that an engineer would use in the back room, like synthesis of embedded software from models, for example, might be something that actually becomes part of the deployed system. You put the synthesis tools in the deployed system and you synthesize revisions of your system as it's running. Okay? That's an interesting twist on the design technology problem. Security and privacy, of course, are a big issue, and energy efficiency. Now, here's the best part of it all. It's the team. Okay? These are the people that are involved. And quite a few of these I knew before we got started, but actually more than half of them I didn't know before we got started on this project. And I think we've got an amazing team here. And so I'd like to just give you a sense of who the people are that are involved. So the Berkeley people, Kubi, right over here, is going to be kind of our chief software architect. That's his job. He's going to solve the software problems in this world. Right, Kubi?
Tomorrow. Right.
Tomorrow. Yeah. I'm going to be the guy who gets all the blame when things don't go right.
Oh, I like this already.
Yeah. Jan's going to be the guy who provides the vision and the excitement. Okay, that's his role. Okay. Alberto's going to solve all the design technology problems. He's going to figure out how to take all those innovations that the EDA world, the electronic design automation world, developed for producing VLSI chips, right? VLSI chips are very much in this classic model, right? A bunch of engineers in a back room throw a whole bunch of technology at doing a design, and they get everything right, and then they do a tape out, okay? And then they get a chip back, and then they ship a product, right? It's a very different kind of design process than the one that we're envisioning in TerraSwarms, where the systems are going to be continually evolving. And yet we believe that many of the technologies that are used in this EDA world are also usable in the field in evolving systems. So online synthesis of revisions of systems. So that's going to be kind of Alberto's bailiwick. Sanjit's job, is Sanjit here? No? Okay, then I can give him any job I want. His job is going to be to make sure these systems are safe, okay? That they don't do things in the physical world that we don't want them to do, okay? That's a little bit distinct from the security problem. He's really going to be focused on making sure that a continuously evolving, self-revising system doesn't have bugs. That's a pretty daunting problem, right? Because it's hard enough to assure that a static design doesn't have bugs, right? But this is going to have to be systems that are evolving, not having bugs and not introducing bugs as they evolve. John, who is here somewhere. Yeah. So John is kind of a chief system architect. That's the way I view him. He's going to figure out how to put all these pieces together, okay? David Wessel, right over here, David has an enormous amount to contribute both in the application space and also in the technology space. David is an expert in getting devices that interact very deeply with the physical world and getting those interacting with the information technology world. Doug Jones from Illinois is an expert on utility-based optimization of systems. So in other words, as you're evolving the design of a system, how do you decide how to evolve it? You want to evolve it in such a way that you maximize utility, minimize cost, minimize risk. And Doug Jones, who has a very strong signal processing background and also a very deep experience with sensor devices and embedded systems, is going to be in charge of that. Tayana, who I think probably some of you know, is from San Diego. She's going to be in charge of our application driver, and I'll tell you about that. She and John together actually are in charge of that, and I'll tell you a little bit about that more in a little bit. So Prabal Dutta and David Blau at Michigan are experts in low-power wireless sensor and actuator devices. So they're going to be people that are going to be very much at the edges of the swarm, where the interactions with the physical world are really occurring. Kevin Fu, who is also at Michigan, is a security expert. And he's a security expert who is particularly focused on embedded systems. And a lot of his prior work has been in embedded technologies in medical systems. And he's going to adapt that to a much broader challenge, not focused just on medical systems, but much more broadly on TerraSwarm systems. So Carl Sechin and Ruzbe Jafari at University of Texas at Dallas are experts in wearable devices, sensors and actuators that you integrate with your clothing and carry around with you in your physical environment without sticking them in your pocket like this and then staring at the screen to interact with them. Carlos Guestrin and Ben Tasker are machine learning experts. These are the guys who are going to figure out how to extract information from these huge volumes of data. And Carlos, in particular, brings to the table a really wonderful infrastructure that he's developed called the Graph Lab, which is it's a machine learning infrastructure that is designed from the start to be able to deal with enormously huge volumes of data and extract information from those enormously huge volumes of data. And his focus has been on architecting a software infrastructure to enable experimentation on the machine learning front. So one of the things we're asking him to do is to adapt that infrastructure that he's developed so that he's not dealing with static bodies of information. So in the past, it's been more about you have a huge chunk of data in a database. You want to get some insights out of it. And the data is static. But in the TerraSwarm's context, it's not going to be like that. You're going to have streams of data coming through all the time. And the interrelationships between the data and the data sources are going to be constantly changing. So the software infrastructure is going to have to be modified to deal with dynamic structures of information rather than static structures. Anthony Rowe is at CMU, and he's one of the key people behind the Sensor Andrew project, which is a software infrastructure, really an API layer around sensors and actuators. It's an API based on XMPP, which is the technology behind a lot of the chat. It originally started with Jabber, okay, and XMPP evolved out of that. And so a lot of the chat services that probably those of you who are under 30 use routinely, and those of you who are over 30 scratch your heads in wonderment. Anyway, Anthony is an expert in an API-level technology that is adapting some of that social networking technology for interacting with sensors and actuators. Richard Murray, Vijay Kumar, and George Papas are control system experts. And these guys have done some exceedingly innovative approaches using control theory in very interesting ways. And in particular, one of the key things that we're hoping that these guys will be able to do is to guide the process of these self-evolving systems. So as the systems are adjusting themselves and changing their structure as they recruit resources, the question is, how do you do that and keep them operating within safe parameters? And these guys have done experiments like that, where they apply control theory concepts in order to get that to happen. Vijay, by the way, is now, he has a part-time job at the White House, at the Office of Science and Technology Management. So we have connections in high places. He got that since we submitted the proposal. And he says he's going to be there for either 4 months or 4 years. He's not sure which. I guess we'll find out next week. But he's going to be working 3 days a week at the White House and 2 days a week at Penn on this project primarily. Vijay also has some absolutely spectacular videos on his website of swarming UAVs, unmanned air vehicles, that are coordinating their actions in a space. And in the videos that he shows on his website, these are all centrally controlled. The interesting twist in Terra swarms is that they need to not be centrally controlled. They need to be interacting with one another and self-organizing. And so he's kind of signed up to use his test bed as an experimental framework to try to make that happen, so that these UAVs are not, in fact, centrally controlled, but are self-organizing. George Papas has done some really beautiful work where he applies control theory to preserving privacy. To me, this is a really interesting approach, right? It's an interesting twist on the privacy and security problem. So this is a phenomenal team, and I'm really excited to be working with these people, and so I hope that many of you will also engage with us. Okay. So what I'd like to do is talk a little bit in more detail about what some of these people are able to bring to the table. Because, as I said, we haven't started work. We're not going to start work until January. We don't have any money right now. We don't have any people. But nonetheless, all of these people have a lot of experience and a lot of background. So, for example, at San Diego, Tayana Simunich-Rosing has been quite central to a project called CitySense that is deploying a bunch of sensor devices like this that are connected to handheld devices that provide the communication infrastructure. And they're using this for environmental monitoring. So they're gathering environmental data and using it to obtain a picture of what's going on within a city environment. Okay, part of her vision is that she would like to be able to use this data to guide traffic patterns, to guide people towards healthier behavior than they might otherwise engage in, things like that. Okay? So we're hoping that we can, in fact, leverage some of Tayana's prior experience, and perhaps most interestingly also just bring some of the infrastructure that she's already built into the project and use it as a test bed for testing out some of the ideas. So we can get Kubi, for example, to try to make his software run and interact with her platform and, you know, provide the app layer, really, for developing the applications that use this sensor data. So I mentioned the Sensor Andrew project, which Anthony Rowe is a leader on. And so I guess I don't really need to say anything more about this. But the key thing is that one of the key ideas here is that this is about providing a layer of abstraction that is trying to correct this problem that Jan diagnosed as the stovepipe problem in today's sensor networks. The fact that we do have sensor and actuator networks around us. So for example, if you build a new building, you can deploy in that new building a single vendor system for controlling the lights, the windows, the HVAC, and all that, right? It'll be a single vendor system sold by Siemens or somebody, all right? And it'll be a pretty much closed system. In fact, when we remodeled the DOP center on the 5th floor of Corey Hall, which was quite some time ago, 15 years ago maybe? I don't remember exactly, but about that. No, the DOP Center, 2000, so 12 years ago. So at that time, we actually spent a lot of money on a very fancy computer-controlled lighting system. Nobody has ever used it for anything And pretty much the only thing we have done with this computer-controlled lighting system is call the manufacturer to come service it when it stopped working. It has otherwise provided nothing, really, to the environment up there. Absolutely nothing, and it was a complete waste of money. And you can't always turn the lights on. Sometimes it decides that it's the middle of the night, and it's actually the middle of the day, and there's these convenient switches that are labeled, what are they labeled? Bypass, the bypass switch, right? So we all know about the bypass switch, which basically tells the computer, damn it, whatever you're trying to do, stop doing it and turn the lights on. So this is a stovepipe system. It's a closed system. There's no way to interact with it, okay? I found the manuals for it. You know, it was 3 binders full of three binders full of paper that had, you know, just impenetrable page after page after page of arcane commands that you had to do at keyboards that were touch-sensitive keyboards, which for the time was pretty cool, but closed system, useless, okay? We got to open these systems up. So a system like Sensor Andrew really provides an API layer, and the idea is now you can develop apps for this, and the app developer doesn't have to be the vendor of the hardware, okay? That's a key idea. So at CMU, Anthony's got a bunch of projects, a smart home project, a body tracking problem. This one's really pretty cool. I mean, this is about, you know, trying to figure out what a person is doing. Obviously, there's privacy concerns here, but one of the interesting things is you'd like to know whether a person has fallen down, okay? That's one of the things that you can do with sensors, and that's pretty important if you have, you know, if you have experience looking after older people. That can be a really big issue. They've done water quality monitoring, people tracking, air quality tracking, like Tayana has done at San Diego, monitoring campus facilities, interacting with building automation systems, because some of them are actually starting to get a little more open than they used to be. Yeah.
What is water quality monitoring? Just out of curiosity, is this like?
You look at pollutants, you look at certain chemicals and stuff.
Yeah, I'm not sure exactly what they're measuring. I would guess maybe lead and you know, heavy metals, but I'm really not sure. We should ask Anthony about that. Right here at Berkeley, we also have an effort that was presented here just a couple of weeks ago, I think, which is this OpenBMS, which is an outcome of the Local project. And OpenBMS, like Sensor Andrew, also has an API layer around sensors and actuators, and it has been hooked up to a very large number of sensors on the Berkeley campus that are monitoring energy usage throughout many of the campus buildings, most of the campus buildings, I think, at this point. And in addition, in some of the buildings in this Local project, they're able to close the loop, and through this same API infrastructure, take that sensor data and actually control the HVAC system. In Sudarcha Dai Hall, right next door, they're able to do this. In fact, I had the pleasure of sitting in on a really dramatic demo when, you know, the sponsors from NSF were visiting and wanted to know what was going on in this project, and we're all sitting around the table, and one of the students, you know, goes to a website that we're all watching and enters some data indicating that that the room, we're uncomfortable in this room. It's too warm, right? So irrespective of sensor data, it's too warm. So the system reacted by immediately bumping up the airflow into the room, and the door slammed shut because the air pressure rose in the room more or less immediately. You know. So yeah. So anyway, this is a project that is going on that we can also leverage in this effort, because it provides us with an experimental test bed that we can use to do experiments with. So for example, in my group, we've been building a rapid prototyping service with this idea of kind of providing an app layer, an app development layer, where you can just throw together some idea that you have that's going to take a bunch of this energy sensor data. So for example, if you have some idea about how you might look for anomalies in energy usage in a building, and you'd like to throw together an app that alerts certain people by email when you detect these anomalies, right? Today, you would have to find yourself an expert programmer to build something like that. We'd like to get it to the point where it doesn't require an expert programmer, that you can really just throw one of those things together and deploy it, okay? There's a bunch of other things. I mentioned Carlos Guestrin's Graph Lab that we're going to be using. David Wessel has a lot of expertise in real-time networking, and I think we're going to be leveraging that because I think that's going to have a big effect on what we can do in these projects. We have a lot of expertise in low-energy sensors, in wearable sensors, in modeling tools, in analysis tools. Kubi's tessellation project gives us a real foot forward on the software architecture for the Terra swarm. And we've got these UAV test beds that the Penn folks have developed that can be used, I think, to put together some pretty daunting, some pretty compelling application examples that would really stress the technology. Now, here we have a chart that is showing the structure of the project in the form that would only appeal to a third quadrant person, okay, which is one of these people who likes to check off milestone boxes on forms, right? So we, of course, will be overseen by third quadrant people, and so we have to organize the project according to a bunch of numbered themes. We managed, SRC wanted us to provide 4 numbers for each task, but we realized, well, we could get by with 3, actually. That was, in fact, there's only 3 levels of hierarchy here. Actually, there's only 2, but we could have done 2. But no, they wanted 4. But anyway, we talked them into 3. But anyway, this is how we're going to be organizing the project. And in particular, this is also going to drive the reporting and the hiring for staffing and so on. So anyone who's working on this project is going to have some responsibility to one of these boxes or more than one of these boxes. Now, I'm not a good guy at this third quadrant stuff, but I actually did get some value for myself in just understanding how we were going to organize this project by looking at these themes. So basically, there's 4 big themes. The theme in the upper left here is going to be the applications, okay? And there we've decided to center on smart cities, in part because we can do anything, and it's going to fall under the heading of smart cities, right? Pretty much. So it gives us an enormous amount of flexibility, which is a good thing. But it's also, there's also some driving functions, okay? So under this smart city theme, we have decided that we actually are going to impose a requirement on applications, okay? And we call this requirement the tale of 2 cities. And the idea is that any application that is developed that we're going to designate a Terra swarm application should have some piece of functionality that provides value in normal times, right, in the best of times, and some piece of functionality that provides value in the worst of times. The same system needs to provide both, okay? So the idea is that if you deploy a sensor network with some actuators that are going to control the HVAC system, for example, are there ways that you can leverage that system to help guide an evacuation in the event of an earthquake, okay? And one of the reasons that I think that it's a really good requirement to impose on the applications, that every application should have at least a dual function like this. This forces the adaptability of these applications. You can't get away with a single stovepipe solution that just does one thing, okay? You're going to have to find some way to get whatever it is, whatever experiment it is you want to do in this project, to be able to adapt to some other scenario that is a bit different from what you consider to be your normal scenario. Okay? So this is a picture of Atlantic City 4 days ago and Atlantic City 2 days ago. And so we do have situations where things change very suddenly, and we'd like to be able to leverage infrastructure in order to be able to make things a little bit better when things go sour. Okay? So that's a big part of that objective in this upper left quadrant. Okay? This application theme is going to be dealing with that kind of duality of problems. The second theme is on platform architectures and operating systems, and a very big part of that is what we're calling the Swarm OS. Okay? This is really going to be the thing that's going to provide the app programming level. It's the framework against which you develop applications. There's sub-problems within that can be segregated out. So resource optimization with dynamic and uncertain access. So in other words, we don't believe that we're going to completely be able to solve the problem of making sensors or actuators perfectly reliable. They're never going to be perfectly reliable, right? They're going to come and go. Moreover, a lot of applications are going to depend on mobility. So you're going to have mobile devices that are going to move into an environment where there are a bunch of sensors and actuator resources, and then they're going to move out of that environment, and they're not going to have those sensor and actuator resources accessible anymore. Okay? So that kind of dynamic structure in the system is going to require mechanisms for doing resource optimization. The networking world is very heterogeneous right now in this sensor and actuator space. There's a huge variety of different things out there, and as a consequence, we think that we're not going to solve that problem. We're not going to homogenize the network. I don't think that really makes sense to try to do. Instead, what we need to do is abstract the network so that network services become services that you can recruit without being particularly tied to the underlying technology in the implementation of that service. Making sensors and actuators into genuine components that you can put together into systems is another big part of this. Trust, roots of trust in sensors and actuators. How do you know that data that you're getting from a sensor is in fact correct? That you're not getting, for example, you're not getting a replay attack, right? Your GPS sensor is reading data from the GPS satellites right now and not reading data from some guy in the room who has in his pocket a little GPS transmitter that is broadcasting yesterday's GPS data or something like that. Okay. So there are things that can be done at the hardware level that can provide some essentially very solid bases for building trust in these systems, and that's what this effort is about. Theme 3 moves up into the network scale and talks about the services that you build out of these things and the interaction with the cloud. So converting these huge volumes of data into actionable information is a big part of this. How do you distill information from data? Okay, this is a big part of where the machine learning guys are going to contribute a lot. Localization continues to be an enormous problem when you're interacting with the physical world. And one of the things that we're going to focus on in this localization effort is not on trying to identify where things are in three-dimensional space. That's the classic localization problem. We're focusing instead on what we call semantic localization, which is deciding where in a conceptual space the object is. So in other words, we don't want to know that my cell phone is at this latitude and longitude. We want to know that it's in this room. Okay? And moreover, it's on this side of the glass, not on the other side of the glass. Okay? That's semantic localization. It's about knowing where in a logical space rather than in a physical space your devices are. So that's going to be the focus of the localization effort. And anyone who has ideas on how to contribute to this, we're very, we're all ears. So control of mobile devices and other dynamic assets also falls in this category. This is where the control theory guys have some really nice ideas about how to use control theory to recruit mobile resources to provide services. And of course, security and privacy preserving techniques. I'll have a little bit more to say about that in a few minutes. The fourth theme then is on methodologies, models, and tools. And a big part about this is to take techniques that have been under development in the design technology world, like programming models and modeling formalisms and contract-based interfaces and platform-based design and all that, and adapt those techniques to this dynamic framework, where, in fact, you're not so much focused on doing, say, synthesis of correct by construction VLSI designs, but rather synthesis of correct by construction alterations in the field of the behavior of some application. Okay, so the synthesis tools get deployed with the applications, and they become part of the ongoing runtime behavior. And of course, doing that in a way that provides some level of assurance. So assurance and verification of in particular, cyber-physical properties, because these systems are interacting with the physical world. Okay, so those are the kind of the four themes under which we're organizing this project. Let me talk just a couple of minutes about the security and privacy question. Okay, so security is a big issue. If you are able to dynamically recruit actuators, that's scary because, well, it depends on what the actuators are, right? Suppose that all of the locks in this building become networked, right? Then some malicious person could lock all the doors and not let us out, or something like that. So we have to prevent that, okay? And there's a key idea here that is kind of a germ of an idea that, to me, was a real revelation. And the key idea is that there's actually something to be said for safety in numbers. That sometimes you can actually make things more secure, more resilient, more robust by having lots of pieces in these systems, okay? That just the mere replication that arises in a system that has many, many components can by itself improve security and privacy, okay? So in particular, one of the ideas in privacy, which was completely new to me, I'd never heard of this before I started working on this project, but differential privacy provides a framework for essentially, so the problem that it's addressing is that you can often take a piece of data that's been collected about a bunch of people, and it's anonymized, so the data is not associated with the names of the individuals. But if you can cross-correlate that data with some other piece of data, okay, the cross-correlations between these can actually reveal identity information, okay? That's a big problem in the privacy world, and it certainly becomes a problem in the TerraSwarm world, where our whole goal is, in fact, to bring this kind of social networks phenomenon of data aggregation to that physical boundary, right? So data aggregation is going to be a big part of this. How do we do that in a way that does not inadvertently compromise privacy? And differential privacy provides a framework for removing this side channel information. And the interesting thing to me about this framework is that in some sense it depends on having large volumes of data. It works better when you have more data than when you have less data, okay? And so it's a good match for this kind of scaling up of a TerraSwarm scenario. So another example, which is, was also a bit of an insight, a breakthrough insight to me. It turns out that tighter coupling of distributed systems can sometimes make them more secure, okay? You would think that would be wrong, right? That in fact, in order to make things more secure and more resilient, you want to loosen the couplings. You want to reduce the dependencies between the systems. But here's a concrete example where tighter coupling actually improves the resilience and the security of systems, which is time synchronization. So time synchronization is something that is happening big time right now. So I think that if you have an Apple computer or phone or anything else, it synchronizes its clock. You never set the clock of this guy, right? It synchronizes it using NTP with a clock in Palo Alto. NTP is pretty sloppy. It's been around for around 20 years. And the clock is synchronized to maybe an accuracy of about 100 milliseconds, so a tenth of a second. The world is changing. I predict that in 5 years, maybe 10 years, if you have a device on the network it will have its clock synchronized to all other devices on the network to within a few nanoseconds. Okay? So devices will all have a common agreement about what the current time of day is if they're on a network. Now, you would think that this is a tighter coupling, and it would increase your vulnerabilities, right? Because now, all right, well, there's protocols that are used to maintain this clock synchronization. Well, aren't those protocols a potential point of attack? Well, it turns out that actually it's not, they are a point of attack, okay, but they're also a point of resilience. So time synchronization alone, for example, can give you a way to detect denial of service attacks and to detect them very early. Because denial of service attacks are fundamentally disruptions of the timing of some service. And if you have no temporal semantics in a system, and you have no agreement about time in a system, you have no basis for actually declaring something to be a denial of service attack. So today, you know, a denial of service attack gets declared when people get frustrated, right? And they're not getting what they thought they should be getting from the system. But if you have time synchronization, you can actually build into these systems very quick identification of these kinds of attacks and reactions to them that can contain the damage that they have. Okay, so these are two examples that I rather like where actually increasing coupling and increasing the number of devices is used to actually improve the security and safety and privacy of these systems. Okay, so I do need to point out that we're not the only people who have observed this phenomenon, right? IBM has got a advertising campaign for, you know, their Smarter Planet initiative, okay? And the key observation here is that there's something different about systems that are cyber and physical, that when there's an interaction between the cyber world and the physical world, that changes things a bit. So I got these slides from Alberto, including the cheesy transitions, okay? But, you know, these come from IBM PR materials, and there's an observation that really this cyber-physical interaction is a big point of action right now in the world. Now, the key thing that I'd like to focus on is that bridging the cyber with the physical world is not a totally trivial thing to do. And I think that we've kind of gotten lulled into a false sense of confidence in this bridge because we've been able to deploy cyber-physical systems that work pretty well. Modern aircraft, for example, the planes that you fly with their fly-by-wire systems are quite sophisticated cyber-physical systems, and they're far more reliable than the airplanes that we were flying, you know, 30 years ago. So we've gotten lulled into a false sense of confidence here because in some sense we're actually trying to bridge two worlds that are really very, very different worlds, right? Computation is intrinsically discrete. Things happen a step at a time. The physical world is not intrinsically discrete. I mean, you could argue about that, right? You could get into some quantum mechanics argument, but useful models of our physical environment are not really discrete models. They're really continuous models. And bridging these two worlds is not an entirely trivial thing to do, and it doesn't, the techniques that we've used so far in these systems like these aircraft don't scale very well. So a concrete example of where we can think in new ways when we talk about bridging the cyber and the physical world is this project that the BWRC directors came up with called the UNPAD, okay? And the idea here is, okay, well, you know, all these handheld tablet devices, that's old stuff, right? They've been around for 20 years, at least at Berkeley. But what's next, okay? Well, let's have our systems interact directly with a physical environment instead of through an information-based screen, right? The interaction here is between my brain and the information technology world, right? Why my brain? And, you know, to the extent that it interacts with other parts of my body, it's my fingers, and it's a rather awkward interaction there, right? So, but the real focus is on the interaction between my brain and the physical and the information technology world. So the UNPAD view is get rid of that digital barrier, okay? and interact with the information technology world much more directly, right? Through motion, through your environment talking to you. So Jan downloaded a bunch of, here are 3 sort of inspirational videos developed by Corning about kind of an unpad vision. Instead of having this thing in your pocket that you carry around with you, right? Information appears when you need it, okay? And you can manipulate that information when you need it, all right? That's a key idea. So here we have, you know, these are kind of devices that are using their knowledge about where they are, how they're interacting with your physical world, and not so much interfaces between your brain and the information technology world, right? They're interacting much more directly with your physical world. Okay. Briefly about the platform idea, right? The idea here is to develop a way for smart people to develop applications. We want these applications to be able to recruit sensors, actuators, networks, storage, and computing. These are the resources that are available. We want them to be able to develop apps that are home security apps or emergency handling, energy efficiency, health monitoring, unpad interactions where you're interacting with the information world through not screens and keyboards, but through your own physical world. And the idea here is that this Swarm OS, which is going to be a big distributed complex system, will provide that application layer. And of course, since Alberto's in the project, we have to identify this as platform-based design with using Alberto's patented hourglass shape. Okay, so I'm going to skip over some of the details of this because I think nobody here will be surprised that the Swarm OS is a non-trivial thing to develop. And I think we can leave that. And I've already said that large numbers can improve security and reliability. I do want to give you one piece of insight, which is also something that I've gotten mostly by having, watching Chris Piester jump up and down and really insist on this, right? If you want to really rile Chris Piester, go up to him and say, wireless is not as reliable as wired networks, right? And get ready to be screamed at. He has some really compelling arguments, actually, that intrinsically wireless can probably be made even more reliable than wired, okay? And that this premise that we have that it's not as reliable as wired networks, I think he really questions. And I think he's onto something. So, okay, so there's our themes. We need to get to work. We don't have any money until January, but we need to get to work anyway. So, thanks very much.
Thank you, Edward. Congratulations on leading a successful proposal. Looks pretty impressive. Questions in the back?
On safety, modern warfare is going to be on electromagnetic burst. You didn't talk about anything about people coming around and doing electromagnetic pulses to down a system and then put it in a safety mode. I think that's going to be the future of safety. I think the next war is going to be fought that way.
Yeah, I think you raise a good point. There's actually things that can be done that are even much more modest than taking out electronics with high energy electromagnetic pulses. So one example is I recently learned actually from one of my students, Ilge, that in the power systems world, there are quite a few systems out there that are relying on GPS to provide a time base for these systems. It's very easy to take out GPS. In fact, you can jam it trivially with a device about this big. I could jam all the GPS receivers within a kilometer with a device about this big, okay? But there's more insidious things that you can do. One of the things that you can do is this, I mentioned earlier, this replay attack. You can make a transmitter that will give you a satellite signal that looks perfectly legitimate, but it happens to be one that you recorded yesterday at some other location. Okay? And your GPS receiver will pick it up and say, you know, okay, it looks like a perfectly legitimate satellite signal. I'll set my clock, and it's not Thursday, it's Wednesday. That's a problem. If you're counting on this system to provide your timing information, timing in the power grid is exceedingly important. Okay? If you're off by 1/120th of a second in the phase that you're generating, then your generator becomes a load, not a generator, right? Because it's exactly out of phase with the other generators, and you can do an enormous amount of damage to the system, right? So there's a lot of vulnerabilities out there. They all have to be considered, okay? I think we don't want to just say, well, okay, you know, electronics can be taken out with electromagnetic pulses, therefore we shouldn't use any electronics. That wouldn't be, I mean, that might be right, but it's not going to happen, right? And so
yeah, I didn't see anything in there putting money forward for that kind of testing in environmental chambers and things like that, like industry does.
yeah, it's true. There is nothing in this project about doing that particular kind of testing. I think that part of it is that this project is not focused at the circuit level. Okay, and in fact, that's a little hard for some of the people in the project who really want to be doing, you know, the next best low-power sensor. But we're trying to get them to move up a little more to the system level and leave the electronics to other people to work on. Yeah.
Great. I like this vision. You really articulated the just wealth of problems that are at hand here. One of the things that was interesting when you were talking about, obviously, that the cloud computing and how a big part of that was people, just the data and the way they could kind of view it in different ways and collage it together and these sort of sharing issues. And I'm thinking about a lot of sensor networks and a lot of these kind of platforms that we've looked at in the past. I think another challenge that's in there that I think you were trying to get at in various ways was that unlike some of the other things like maybe apps we have on mobile phones or other traditional kinds of platforms that have had a lot of growth with sharing, is that they're more personal, like people sharing photos or people sharing stories. So it's driven by people wanting to share data. So even something like text messaging is kind of, from an engineering standpoint, kind of a boring system, but from a social standpoint, of huge value. So it might be this, we don't know what the kind of killer social application is for this landscape, but I could tell that might drive it, because even the systems that you showed and the ones that I'm aware of myself, that they are more infrastructure from kind of industry standpoint, and they solve a lot of really compelling problems there. But I'm sort of still seeking out, and you hinted at some really good ones in there, but I think that's going to be a really exciting place to kind of hedge some bets about that.
Yeah, I think that's a really good insight, and one of the things, you know, with regard to, for example, dealing with the privacy question, I think that, you know, a lot of people talk about how many people who use these social networking applications are voluntarily giving up huge amounts of privacy, but they're doing it because they perceive value that they're getting from it. And in this TerraSwarm's context, we're actually talking about technologies that will put people at similar risk of giving up privacy, but without necessarily the immediately visible personal benefits. And that's a much more problematic situation. So I think that does create some pretty big challenges. Yeah, we'd love to get your help with this. You're the right guy.
Many opportunities.
So going up way above the circuit level, in theme 1, I guess it's your integrative theme.
Right.
Do you have, what kind of commitments do you have to any domain expert who would have a vested interest in the success of an augmented application, or especially looking at the platform aspect, but someone whose feet are in the domain of municipal activity. And I'm sort of thinking of kind of roughly like Code for America works with municipalities in an open data framework.
Right.
Very roughly. In any case, they have clients who are very interested in solutions, and however, this project has to come up with some solutions that are suggestive of generality, not just pinpoint use.
Yeah, you raise an excellent point. Are you in a position to help us connect with these people? No? Okay, let's talk. Yeah, because we'd be very interested in doing that. There's always a risk, of course, when you're developing a platform technology. You can't necessarily deploy applications at scale right away, right? So, but you need to understand where the potential applications are, and I think you're right. And so, yes, we would very much like to connect with people like that. I think right now, to be fair, in the project we have very strong industry connections, but they're much more on the vendors of the hardware, and not quite so much with the people who would be the buyers of that hardware that would deploy it in a city, for example.
Other questions or comments? If not, well, thank you once again, Edward.